Hello everyone, this is Harsha. Welcome to Finite Element online course for geotechnical engineers. I'm Harsha, I'm a geotechnical engineer at MIDAS IT. A very warm welcome to all of you and greetings once again everyone. So I hope you are enjoying this Finite Element online course for geotechnical engineers held by MIDAS IT South Korea. So in this session, we'll be dealing with the fundamentals of seismic analysis, and I will be hosting this session for you today. So the very first one, maybe I'm going to introduce you with the dynamic analysis. So in the first case, as I said, there's a building and the soil continuum which I'm going to model. I will be dealing with the soil structure interaction. So what is soil structure interaction? And what are ground motions, and then the importance of dynamic analysis, why this dynamic analysis is important, and then we'll deal with the seismic soil structure interaction. Later on, what are the different types of dynamic analysis? We'll be dealing with these topics in the first slides. And then later on, we'll be opening like a software and we'll model the building along with the soil continuum. So before going into the software, I'll be describing you what is the model that I'm going to do it and the workflow corresponding the same. And then I will be giving you a brief idea about the infinite boundary conditions that are required for dynamic analysis or seismic analysis in any finite element software, especially in GTS NX. And then in the next category is the analysis and the output. Here, the first analysis which we do is an eigenvalue analysis, where we find the frequencies, model 1 frequency and model 2 frequencies of the model that we do, and then we interpret those results, and then later on we use it to calculate a mass and stiffness proportional coefficients. Then we will apply seismic load, and then we run the nonlinear time history analysis to find the accelerations, basically the amplification, how it has been done when the wave propagates through, and the displacement. Later on, the important thing is the additional tools that are present in GTS NX, how that will help you to enhance your dynamic analysis. So all those additional tools will be dealt with. And lastly, we'll discuss about the bridge abutment, so the certification task. So here we'll provide you with a tutorial tomorrow, and the seismic analysis of the bridge abutment will be given to you. I hope that helps you in easy modeling of dynamic analysis in GDS NX. So let's brush up our mind with the theory which I'm going to present now. So as I said at first, the soil structure interaction. So introduction to dynamic analysis, and at first we'll see what is soil structure interaction. So what is soil structure interaction? The name itself suggests it's an interaction between a soil and a structure. It's basically the interaction of stiffness and deformation between the soil and the structure. So why is it important? So how we can like consider the soil structure interaction in a regular structural scenarios, structural software is what we do is we generally apply springs to the foundations of the building or a bridge. So that foundation, that springs may be your linear springs or non-linear springs or multilinear springs. So there are different types, and that's nothing but instead of providing your fixed supports or pin supports to your building foundation, we are doing n springs. So that's a sort of interaction which we are describing to the building foundation. But what happens is this, as the behavior of your soil changes, because as a soil resists your load from the superstructure, and when the behavior of the soil changes, the load on your superstructure changes. For example, like if the soil behavior changes, in case of a bridge, the forces in the deck will also change. That means soil is actually governing the principle, governing the design in here. So this soil structure interaction, as I said, is important, but how this seismic soil structure interaction affects the design and how it should be considered, will be dealing with that in the coming slides. Ground motions. So the ground motions is nothing but the movement of your ground, because of the dynamic load. That dynamic load can be either earthquake or a blasting load. And as you know, the dynamic load, such as earthquake, occurs because of a sudden slip on a fault, and the load because of blasting, and all these dynamic loads will result in generation of waves those are body waves and the surface waves, and these waves in turn create motions. And here the motion on the bedrock is nothing but your bedrock motion. If that bedrock is exposed to atmosphere, then the motion on that bedrock is called rock outcropping motion. And the motion on the surface of the soil is considered as free surface motion. So these are the basic ground motion, and this will help our understanding in the next slides. So as I said, why dynamic analysis is important, and why should we do it? So here you can see a building. So this is a building resting on your soil. So what happens in regular analysis is we don't model a soil continuum. We just model a building and the foundation, and then we apply the soil as a springs to the foundation. And then we run the different loading conditions, like the earthquake load, the wind load, and then all the static loads. And we do a proper codal combinations of loads, and then we go for design. That's as simple as that. But like for earthquake loads, we do run response spectrum analysis, and in some cases we go for time history analysis. But important thing is we need to consider the effects of your soil continuum as well. So because of the earthquake, the waves propagate that you already know, and because of those wave propagation, it affects your soil as well. So what are the effects is the soil itself has some dynamic properties, such as we'll discuss them in the coming slides. And those dynamic properties affects the wave propagation. And because of the nature of the soil itself, and due to the earthquake, that soil can be turning into liquefiable soil. So a sort of liquefaction can also come. So let's say here we have a source. This is the source of earthquake, let's say focal point. And because of because of this sudden slip in the fault, the waves generate, and these waves are nothing but body waves, and as they interact with the surface, we have a surface waves. And due to the travel path, it have its own effect because of the travel path. That's what we call it as a radiation damping. And because of the site condition, again, that's nothing but because of the properties of the soil, again the propagation of the waves changes. So as the wave reaches the surface, the amplitude of the wave is more when compared to the amplitude when it is at the bedrock level. So because of the soil properties, it has been changed, and now it will apply more force on your building. So that's why it's recommended to run a seismic soil structure interaction analysis, at least for important structures. And now we'll see if there is a sand layer over here, and it's completely saturated, and because of the earthquake load, there is a high probability of increasing the pore pressure drastically, and that may result in liquefaction. And in many cases of building design for foundation, we generally neglect the liquefiable layer and will proceed for analysis. But as you know, as the soil behavior changes, the effect of load being applied on your building changes drastically. So as we are talking about dynamic loads, there are some other dynamic loads such as the train vibration loads, the blasting loads, the vehicular vibration loads, and the machine foundation. So there are many dynamic loads. So these loads will actually affect the buildings or the superstructures. So it is recommended to go for the dynamic analysis considering the soil continuum, at least for important structures. So here we have this is a seismic soil structure interaction which we are going to deal in this slide. Here there is an incoming wave, and this is a bedrock. It is exposed to atmosphere, and here we have a bedrock, and over this bedrock we have a soil layer. And on the soil layer we have a buildings. Yeah, now we have an incoming motion, and this motion actually propagates through a bedrock, and the amplitude on the bedrock, that nothing but your rock outcropping motion, is lesser than the amplitude from the surface, because soil is very much having lower stiffness when compared to rock. So the amplitude is very much higher when the wave propagates through when the incoming wave propagates through the soil. And this propagation is highly affected because of soil properties. Those we call it as dynamic soil properties. And the major properties that affect your wave propagation are nothing but the important dynamic properties are unit weight, shear modulus, damping ratio, and Poisson's ratio. So here, as the incoming wave reaches the surface, its amplitude is much higher. That means it got amplified. Now, and now this load has to travel through your building as well. And at the top point of the building, the amplitude of the wave will be even higher when compared to the building, when compared to the wave on the surface. So that's all pretty normal. But now, we have a design acceleration, and we cannot directly apply this design acceleration underneath your building and go for the design. At least we need to model the surface layers to which we have an input properties, and then we can apply the design acceleration by converting that design acceleration to the depth of the model or till the bedrock. So what I meant to say is it's always better to model a building along with the soil layer. So we cannot directly apply the design acceleration either underneath your building or underneath your soil layer directly. We need to convert this design acceleration into bedrock motion. So you can apply the at the bedrock motion and then model the soil layers, and you can get the effect on the building. So this process of converting your design acceleration into bedrock motion is called deconvolution. So either you model your building and soil till the bedrock level, or to the soil level depth to which you have a data, and then you convert the design acceleration either to bedrock level or to the level to which you are modeling, and then run the analysis. So this will provide us with more idea about the behavior of your building by considering your soil seismic soil structure interaction. So this will be providing you much idea about the behavior of the building, and it's very important at least to consider it for important structure. And now there are different types of dynamic analysis, and we have three categories at first. In terms of modeling method, we can, in terms of modeling method, this dynamic analysis are of two types. One is substructure method, and the other is a direct method. In the substructure method, what we do is we only model a building, and if the soil is modeled as sand springs in here. And in the direct method, we model the soil and the building on a whole. And in the analysis method, we have a frequency domain and a time domain analysis. In the material non-linearity, we have a linear material, we have equivalent linear material, and we have non-linear material. So all these analysis can be done in GTS NX. But the very first substructure method can be partially done in GTS NX because in this method we have different load combinations based on codal provisions and the springs that has to be modeled accordingly. The springs can be linear springs or multilinear springs and so on. You can define them, but it's always better to go for structural software, as GTS NX doesn't have any codal provisions for building design or a bridge design. So for more classifications, here we have. So in terms of time domain analysis, we have a model superposition method and a direct integration method. So this model superposition is widely required and preferable for structural analysis, where the model participation factor is higher. But when you consider the building and soil as a whole, it's always lesser. The model participation factor, that means mass participation factor, will always be lower when compared to just a building as a whole. So in a frequency domain, we have a 2D equivalent linear analysis, a response spectrum analysis, and a free field analysis. So this free field analysis is nothing but 1D ground response analysis. Here, we do not consider any interaction between the soil and the structure. We just model the soil layers and we'll see how the amplification of the input wave happens when it reaches the surface. It's a 1D ground response analysis, basically. Here there won't be any interaction between soil and the structure. And then we have advanced analysis when compared to free field. It is a 2D equivalent linear analysis. Here we run a 2D equivalent linear analysis. The name itself represents you that it's equivalent linear material, and we run equivalent linear analysis. So the strain compatibility equations such as your modulus reduction curve and damping ratios will play a key role in here. The same inputs plays a key role in free field analysis as well. But this is applicable for 2D, where you can model your structure, but it's applicable only for 2D. So in response spectrum, which is linear in nature, is helpful. You can model run the response spectrum by considering your superstructure along with the soil as well, but it is not recommended. As response spectrum is linear, it is more preferable to run for structures. When you go for soil structure interaction and considering seismic, it is always preferable to go for direct integration method, and the nonlinear or linear direct integration method is preferable, which is a time domain analysis method. And now in terms of material nonlinearity, we have a linear material, we have equivalent linear material, and we have nonlinear material. So in the nonlinearity, again, we have material nonlinear, geometric nonlinear, and the contact nonlinear. So all these three nonlinearities can be considered in GTS NX. So as a whole, GTS NX is a highly equipped dynamic analysis tool. You can do free field analysis, equivalent linear analysis, or time history analysis, or response spectrum analysis by considering all the material nonlinearities. So that's the theory which I wanted you to know. And then now we'll see the model description. What is the model that I'm going to do in front of you, and then we'll describe what are the different infinite boundaries that are possible in GTS NX and on a whole. Yeah, so this is a model which I'm going to model in front of you in today's session. So here we have a multi-storied building, and we are not modeling this building in in the software, but we are importing this building from MIDAS Gen. That's a structural software from MIDAS, and on this building is resting on the soil, and we are modeling this soil in GTS NX, and onto this soil we are going to apply a ground acceleration. So we are going to apply this ground acceleration, and as you know, infinite boundary conditions are required every time when you go for seismic analysis. Hence, I'm applying a free field condition. This is your free field conditions. and what is this free field element, and what are the different dynamic boundary conditions. So we'll be dealing with these dynamic boundary conditions in the upcoming slides. So this is a workflow that has to be considered in GTS NX, or this is a basic workflow in any finite element software as well. So at first we need to model a geometry. Either you can import a geometry or create a geometry. So in this current session, we are importing a building and then creating a geometry of soil. And since the building is completely imported, so its material and its corresponding properties will also get imported automatically. So we need to care about the creation of material for soil. So we need to create a material for soil, and then we need to assign solid property to the soil layer, and then we are going to mesh the soil property geometry with the property that we define, and then we will mesh the geometry followed by loads and boundary conditions. So in the loads, we are going to apply the ground acceleration, and we are also going to apply the infinite boundaries such as free field element in this session, as well as the certification task that I'm going to provide you. And then we will analyze the current scenario, and then we'll see what are the different results. So in the analysis, we'll be solving eigenvalue analysis and nonlinear time history analysis. So this is a building which we are going to import from MIDAS Gen, and underneath this building, we'll be modeling a soil. So this is what we are going to do it in GTS NX, and then this soil will be meshed and by applying the free field elements. So these are your free field elements. So as I'm talking about the free field and dynamic boundary conditions, so we'll discuss about the dynamic conditions now. So there are different types of dynamic boundary conditions. So first, suppose let's say we have a structure and which is followed by a ground soil, and for a static boundary conditions, nothing but your roller support and at the bridge on the fixed condition underneath the model. So roller conditions on your vertical boundaries, so which we call it as a static boundary conditions. So when we apply a static boundary conditions for an incoming wave, the ground acceleration basically. So this wave propagates, and when it reaches the boundary, it will get reflect back. But in reality, we have an infinite ground, and all the wave travels through your infinite ground. It won't get reflect back unless until there is certain in situ conditions over there. So here we need to model an infinite boundaries. So we cannot stick on to the static boundary conditions, as the reflection takes place, and the effects on your structure will be even higher. So we cannot consider them. So in that case, we need to model the infinite boundaries. And more importantly, the first thing we need to do is we need to absorb the reflected waves. The reflected waves should not be sent back. The waves should not be sent back. So we need to absorb all the waves that are coming to the boundary. So here we need to go for infinite boundary, basically free field motion or viscous condition should be provided. And in the bottom, either we go for a rigid half space or elastic half space. And here, these are the three different boundaries that are present in GTS NX. One is a viscous boundary, which I'm then noting you here. This viscous boundary is not an infinite boundary, but it absorbs the waves at the boundary. So hence, it is okay for dynamic analysis. And the second one is a free field boundary. It is an infinite boundary condition where it can absorb the reflected wave, and we'll discuss in details in the coming slides. And we have a transmitting boundary which is applicable only for 2D equivalent linear analysis. So here we have a viscous boundary. So all the vertical boundaries and the bottom boundaries underneath here, all the boundary nodes all the vertical boundary nodes will be applied with the mass and spring and dashpot system. So here, all the waves that are coming to your spring and dashpot will get absorbed. So here, there is no reflection of the waves, so which will solve our initial purpose. Here, the spring constants can be calculated based on these equations directly and automatically in GTS NX. So with the 2 to 3 clicks, you can model viscous boundary in GTS NX. And then the dashboard can be calculated using these formulas, and this will help you in modeling the viscous boundary easily. With just 2 to 3 clicks, you can able to model the viscous boundaries. And now the free field conditions. As I said, in viscous boundaries, it was not an infinite boundary condition, but free field is an infinite boundary condition. So what is the difference? Will let you know in this slide. So basically, we need to model an infinite condition to eliminate the reflections of the wave. So since we cannot model the entire infinite boundary, we need to simulate that infinite boundary using the free field condition. So this is a free field condition. The seismic wave, which starts from the bottom, let's say ground acceleration, which propagates through your domain. When it reaches the boundary, it gets absorbed by your a dashboard that is provided. But this is similar to your viscous boundary, but the important thing in here is this free field can able to propagate the wave. That means the wave can propagate through your free field element, which is not possible in viscous boundary condition. So hence free field will serve the property of infinite boundary condition, where the propagation of waves can be there. So when a wave propagates through your free field element, this can get transferred back to your main domain, which means it's not the reflected wave, but the wave that are propagated through your free field. So as I said here, yeah. So in the viscous boundary conditions, we are not actually modeling we are not modeling the infinite boundary, but what we do is at each and every node of your vertical boundary conditions, we are assigning the spring and dashboard system. But in case of free field, we are simulating this infinite boundary condition. So similarly here as well, sorry, yeah. So we are simulating this infinite boundary conditions by modeling your free field element in the dynamic analysis. So this will serve your purpose of eliminating the reflection waves, as well as creation of infinite boundary by propagating the waves through the infinite boundary. So this is our main purpose. And now we'll see the comparison of different results by considering different waves. Sorry, by considering different dynamic conditions. So here, let's say none, that means no dynamic boundary has been applied. In that case, you can see the behavior is abnormal, which is why we need to go for the infinite boundary conditions. If you want to model the infinite ground, that means you model the ground with which is having the length and breadth of very high. Instead of modeling the 10 meter of the ground, you go for 100 to 200 meters of the ground, which will increase your time of analysis and is not recommended, and it's not required as well. So if you go for infinite modeling, then you have the propagation of red wave. The red color is underneath your purple color over here, and this free field is completely matching with your infinite ground conditions. So hence it's okay, and it's in good agreement with your infinite ground. Hence it's always recommended to go for free field condition. But in some cases, it's better to go for viscous boundary condition as well. So in terms of viscous boundary, when you apply it, you can see the behavior, how it is changing. This behavior is because there is no propagation of waves in the viscous boundary. It's just eliminating the reflected waves. Hence, you can see the change in your the results over here. So this is the result comparison, and hence we are going to model the free field condition in this current session. Sorry. And apart from that, we have one more boundary condition called transmitting boundary. So this is applicable to 2D equivalent linear analysis, and it also simulates the elastic. It simulates both elastic half space and semi-infinite ground layer by setting the virtual slip surface perpendicular to the horizontally layered ground. So this is similar to your free field condition, and more importantly, this eliminates the flaws of viscous boundary condition. That means it can able to propagate all types of material and surface waves. Hence, but the only thing is, this is only applicable for 2D equivalent linear analysis in GTS NX. And now let's start modeling. So I will take you to the software and will model a building along with the soil continuum, which has been described to you in the previous slides. So let's start modeling. So this is GTS NX. So whenever you open GTS NX, it will ask you to choose among the type of models. Either you go for 3D modeling, 2D modeling, or axisymmetric modeling. So as you know, GTS NX is the platform which provides you with all the three kinds of modeling under one platform. So this is GTS NX for you. So let's go for 3D modeling. So we are going to model a building as said earlier, and then the soil underneath it. Yeah, let's proceed for modeling. So now we went for 3D modeling, 3D modeling, and we have the interface in front of us. This is the work plane. So that right now it is in a ZX plane. Let me shift to XY work plane. So this is the horizontal work plane for us. And as in terms of setting, you can see the gravity direction is a set. That means minus Z is a gravity direction. And as I said, the building, we are going to import it from MIDAS Gen. So here, this is MIDAS Gen software, which is the analysis and design tool for the buildings and the industrial structures. So what I'm going to do is, um, I'm going to export this building to GTS NX. So for that, what we need to do is we need to go to export option in MIDAS Gen, and you just click on MIDAS MXT file. And later on, after analysis, you can even take back the nodal loads as well. That means the reaction loads at each and every point of your pile. You can take back to the MIDAS GTS NX. So here you can see this is a building, and we have foundations along with this, and we have some car parking area as well, I guess so, and the corresponding columns as well. So right now I'm exporting the entire model to GTS NX. So I have already created an MXT file, and then so as I said, once you run the analysis, you may get reactions at each and every node of your foundation for different load combinations. You can even export those load combinations to GTS NX. So I have done that as well. So in order to export your combination results, you need to go for nodal results, and you can see in the bracket for GTS. So right now I'm just closing this one and go to GTS NX icon in the top. Go to import, and here we have main MXT file which has been exported from MIDAS Gen. So this is the model. Right now the model is getting imported. In the MIDAS Gen, we can find that model being applied with the springs over here. So you can see those springs, and those springs actually not supporting GTS NX. So hence you can find the error over here. But now we are not actually interested in these springs. We are going to consider the structure on a whole, right? So no need to so we are going to model the soil as a continuum, and then that soil will be in contact with your foundation. So no need to worry about the springs. So we will be deleting those springs with us. And here you have loads being imported as well. So we have different loads. You can find the loads, the self-weight, dead load, and live load has been imported. And as I said, I have the nodal combination results with me as well. So what I do is I will go to import again. Here, import nodal results. So just importing all the results. So here we have all the nodal results with me. And at each and every point you can find the x direction, y direction, and z direction results. So the resultant force has been imported, hence you can see an angular reaction. So we'll do the we'll delete the unwanted things now. So just hide your loads, and here we have a point spring. So just delete the point spring, and then you can see in MIDAS Gen underneath your we have underneath your columns, we have fixed supports. So generally there might be a footing over there, but they haven't considered that. So we will also not consider any a connection between your columns at the car parking area with the soil. So hence I'm going to keep this supports like that only. So now we need to model the soil. So now the building has been imported. Let's model this soil. At first, I will go to the XY work plane. So the grid size by default is 20 meter. I would like to change that to 10 meter. So let's say okay. And let's have an area of soil to be like 90 by 60 meter. So this is the area of soil that I would like to model. So this is a random area which I have taken to be on a precise note. What we need to do is we need to run a simple nonlinear static analysis or analysis, and we need to see that the boundaries of your model is having no impact on the structural results. So till then we need to increase the boundary. So right now this is just an webinar where I'm showing you the procedure. So hence this is okay. Now let's extrude the layer. So here this is my direction and this is the extrusion length, and let's change provide the length of around 25 meter, the minus 25 meter, and just preview it. Yeah, so this is my soil layer, and let's say okay. And important thing in here is the nodal connection between your soil and your raft, as well as the pile foundations. So what I do is I will just hide your foundation, soil here, and we have pile nodes over here. I'm going to have nodal to nodal connectivity between pile nodes and soil. And we have a raft as well. I'm not interested in the connectivity between raft and soil. Let's say raft is in air and entire load is being transferred to the soil through piles only. So that's our basic assumption in this tutorial. If you want to convert, if you want to have a nodal connectivity with raft, then you need to follow the same procedure like what I'm doing now. So right now I'm going to convert all the nodes of the building. So these are the nodes of the building, of the pile foundation, not the entire building, just the pile foundation nodes. I'm just converting these nodes to the points. So now I have points at all locations of the node. So while meshing soil area, I will ask the software to consider these points. So that's the basic assumption which I'm considering. Not assumption, just the basic trick I'm doing. So here we have a solid with us. So our first step is to generate the geometry. So geometric modeling is done. And if you wanted to have a connectivity between raft and soil, then you need to convert the raft nodes into points as well. But as of now, it's not an important thing to do for this session. So let's go for material definition. Since we imported the building from MIDAS, or the building materials has also been imported, but we'll be modeling the soil for you. So here, I'm considering Moculum material. Let's name the soil. Let's name it as soil. And then elastic modulus is 50,000 kilonewton per meter square. Unit weight as 20, and is saturated unit weight as 21. And this plays an important role. So you need to concentrate on the permeability conditions and the void ratio. So what I'm considering is initial void ratio to be 0.5 and permeability coefficients as 1 into 10 power 5 meter per second in all the directions. So since if you want to consider liquefaction analysis, then it is important to consider the porous property. But for now, I'm just running on a dry condition. So all the properties which in this tab are not at all an important thing. Cohesion of 30 kilonewton per meter square, friction angle of 36. Let's say okay. And next, define this soil as a 3D solid property. So select the soil layer and give the name as soil once again. The soil has been done. And now we are done with the meshing. We are done with material and properties. So what I do is I will be meshing the soil layer now. So this is your model. Go for 3D. Select your soil. Let's give a size of around 1.5 meter and go for hybrid measure. Give the name as soil and go to advanced options. So here we're going to consider all the points that we have created. So here we have all the points with us. So select all the points. And these points should get imprinted on the face of the solid. So imprint them and then say okay. So when you say okay, the meshing starts. So here the meshing will take control. Meshing will automatically connect each and every point of your pile with the soil. So this may take a few seconds. So once meshing is done, we will provide the infinite boundary conditions, and then we will do we do apply ground acceleration, and then we have imported a mass from we have imported the reactions from a MIDAS Gen 2 GTS NX, right? So we will be converting that reactions into mass. So since this is an dynamic solver, the reactions cannot be applied as a load in kilonewtons. It should be applied as a mass. So we need to convert them and then go for applications. So yeah, we have a model generated with this. So this is your soil model, and software itself will take care of connectivity between pile and the soil. So you can even check by hiding each and every element and go for checking. As I haven't considered the raft connection, so you can see there is no connectivity between raft and soil. So which is what we wanted. Now let's go for boundary conditions. So at first we already have a self-weight defined. We have a self-weight over here. And now free field boundary conditions. So here we have a free field boundary condition with this. So since this is a 2D free field, we need to go for plane and give the name as a free field and say okay. And now select all the vertical boundaries. So just say okay. Now a free field element is being created on all the sides of your model. So now the bottom condition needs to be generated. An important thing is I forgot to mention while creating the material is the damping ratio. So here by default the damping ratio which I'm considering is 5%. This ratio will be used for Rayleigh damping calculations. So as you know, the Rayleigh damping calculations will help you in calculation of mass proportional coefficient and stiffness proportional coefficient. So now we are done with infinite boundary conditions development. So first suppose I'm going to have elastic half space being generated over here. In that case, what I need to do is I need to create a spring and damper conditions at the bottom. In order to create spring and damper, I need to go to the create option over here. Just select other tab. In the other tab, you need to consider the point spring. So here we have many point springs, but what you need to do is you need to input your K values and then the damping coefficients as well. So this will act like your it will act like your elastic half space. But in this model, I'm going to consider like a rigid half space. So go for constraints, advanced, and auto. Since in my model I applied a free field element, and as you know, the wave propagates through free field element as well. So I need to consider the bottom nodes of the like free field element as well. So give the name as fixed bottom and say okay. So this is my model on a whole, and we need to change the loads that we have imported from a MIDAS gen to a mass over here now. So here we have the loads. So this is the load. You can change the size of the arrows. That's another thing for visualization purpose. So now go to dynamic analysis. Here we have a load to mass conversion. You can choose this load case which has been imported from MIDAS gen, and you can ask the software to convert it into mass. So now you have a mass that has been created. So I will just hide all the load sets along with the yeah. So along so here you can see all the mass. So your reaction has been converted into mass and you can see the entire mass in terms of tons. It's around a ton of 14 tons, and the mass center can also be seen in the properties over here. So now let's proceed for analysis. So that's it. The modeling is done. But one more important thing is we need to go for eigenvalue analysis at first, and then we need to take the frequencies out, and using those frequencies, we will run a time history analysis. Yeah. So just go for analysis. Go to general, and let's go for eigenvalue, and ask the software to take all the load sets. So here we have plain free field condition, load to mass, your building, and we have a soil. So BC set one is nothing but the fixed condition underneath your columns of the car, let's say car parking or something like that. And then we have a fixed bottom. So give the name as eigenvalue and go to analysis control. Here, this number of modes plays a key role. As you know, in structures we have a different codal provisions in many countries that the mass participation factor should not be less than 90% in case of structures. But here, when you model a soil and structure on a whole, it's it's very unlikely to find 90% of a model participation factor. So we come across participation up to based on the model. So 70% or 80%. If it's close to one, yeah, that's good to proceed ahead. So now let's provide a 50 modes and a stream sequence check as well. If you are not activating this, then the software may lose some the eigenvalue calculations in some cases. So consider this one. And if you want to consider instead of if you don't want to consider lumped mass system, then you can go for continuous mass by using this coupled mass calculation. But right now, let it be lumped mass calculation, and let's say okay. So now eigenvalue analysis has been created. Just go to perform and press OK to let the software perform eigenvalue analysis. But I already created a model with me. So this is the model that was already modeled and analyzed. So here we have eigenvalue analysis results with us. So we'll see the eigenvalue results, and then I will let you know how to use that eigenvalue results with us with time history analysis. So we have three tables with us: a real eigenvalue, where you can find the cycles and periods, the model frequency and periods, and we have a model effective mass. In which mode, what is the mass that is being activated, and we have percentage model effective mass. So here we have different modes. I asked the software to go for 60 modes in this model, and here we have a total frequency of around 76.33. So this is a model participation factor. In many codes for structural scenarios, it should not be less than 90%. But since we are modeling a soil with this, since it is more or less equal, sorry, it's 70%, which is higher, and it's like around 24% less than 100. So that's okay. And we need to consider T1 directions, because we have applied the load in X direction. So we are going to apply the ground acceleration in X direction. So hence the X direction is a T1, T2 is Y direction, and T3 is Z direction. So let's consider T1, and we need to consider two modes which are having higher effective mass participation. So here we have many values with us. At third node, we have 24.59. So that is our first model, mode 1. So 3 is your mode 1, and 4 is around 15.8%. That is your mode 2. So 3 and 4, you're having a mode 1 and mode 2, and so you don't have any other value close to that. So 3 and 4 are your mode 1 and mode 2. So just remember the mode numbers 3 and 4. And we go up in the eigenvalues. Here you have 3 and 4. So in 3 and 4, you have corresponding to 3 and 4 mode numbers, you note down the cycles and period. So here for first mode, you have a 1.302865, and then 1.34415. These are cycles per second. So these values are your frequencies. So we need to record these values and use these values in calculation of Rayleigh mass and the stiffness proportional coefficients. And just remember these values, we will use them in the analysis. So here, just go to the model that we are preparing. And now we need to apply some ground acceleration. So here we have a ground acceleration. So as I said, I'm going to apply a load in X direction. So go for X direction and go to time function. GTS NX has a huge collection of earthquake data. You can use earthquake data from these for your projects or for your calibration results and much more. At first, I'm going to consider, let's say, park field 40 degrees and say OK. So here the results are in terms of g, that means normalized acceleration, and you can see the maximum value here is somewhere like around 0.23, 0.24 g. So that's the peak acceleration. So when you run the analysis, you can find more than that on the surface of your soil, and if you on the building, it will be even higher. So let's say OK. So you can even apply the sinusoidal load. You have this equation. So apply your coefficients accordingly and get the sinusoidal wave. Now just activate your function. So this is the function that we need to put here. And now let's go to one more thing I forgot to say is as the time steps plays an important role in the analysis. And here you can see the time step is like around 0.02. That means for every 0.02 seconds, the acceleration is getting updated. So we need to make sure that all these accelerations are taking into picture, and hence a minimum value should be 0.02. And for best results, it is recommended to go for 0.02 upon 2. That means 0.01. So half of your time step should be considered for analysis for better results. So let's go for creation of a time history analysis. We have a nonlinear time history. So ask the software to take all the loads, dynamic load and bottom conditions and so on. Give the name as time history. But these are the time steps that are important. So give the name as park 40 degrees. And let's say we are running the analysis for 15 seconds, and the time increment here you need to provide 0.01 seconds for better results. In order, if you have less time for completion of analysis, you can go for 0.02 seconds, but these time steps generally govern your results. So let's say add. So you have total of 750 steps. And now go to analysis control. So since it's a horizontal soil layer, you can consider a K0 condition. And because of sulfate, whatever settlement that is being calculating in the analysis, I'm going to clear that displacement. Now go to dynamic. So here is where the model frequencies comes into picture. So here we need to calculate mass proportional coefficient and stiffness proportional coefficient, basically alpha and beta. So now I have frequencies for mode 1 and mode 2. So first mode is 1.302865 there, and then 1.34415. And then this is the damping ratio, relic damping ratio, 0.05 seconds. If you want to consider, if you have material damping, different material damping for each and every soil layer, then you can ask the software to consider material damping like how it is. So for for E250 material, we have 2%, and the alpha and beta coefficients are different. So if you want to consider same damping ratio for all the cases, then it's not required to consider the material damping. So let's say OK and say OK. And here in the output control, you can regulate the results to be printed in the analysis. So as you know, finite element results, finite element analysis results in too many results. So you can uncheck check the required ones. So I want acceleration, I want velocity, I'm not interested in reaction force at each and every node. I'm also not interested in applied load. I'm interested in displacement. Let's say I'm interested in strain. So we can choose among the results. So this will reduce the space to be considered for each and every analysis in your CPU, in your computer. So let's say OK and say OK. So that's how the analysis need to be started now. So just go to perform, just tick the time history and say OK. So since I have already done the analysis, I will show the results in this model. But before going for results, I would like to show you the ground acceleration. Haven't considered Park 40 degrees, but I have considered Hachino earthquake. So here, this is the Hachino earthquake. So the peak acceleration is around 0.13 g. So we'll see how the result varied accordingly. So I'm interested in finding accelerations at the bottom node on the ground surface and at the top of the boundary, top of the building. Sorry. So just go for absolute maximum. I'm interested in accelerations at first. So let's consider Tx acceleration. Since I applied a load in x direction, go for Tx acceleration. Yeah, so here you can see the maximum acceleration where you can find is on the top. It's huge. It's 24 meter per second square, which cannot be happened in reality. But why it is happening in the model is here you can see this is a roof which is not actually supported well. You don't have dampers, you don't have proper connections as well. Hence, you can find more and more and more acceleration over there. If I play a video, you can find clearly what's actually happening. So let's select all the time steps and then ask the software to play a video. Oh, sorry. I will change the undeformed view to the deformed view so that will help you to understand what is exactly happening in the model. Yeah, this is a deformed shape. So here you can see the top, the roof is not actually stable. And because of the force coming from top to bottom to the top of your surface, and then when it goes through the building and when it reaches the top, it is actually going haywire. And now I'm not interested to find the results of this roof. So what I do is I will hide the elements of the roof. Yep. So now we can have some proper simulation. So here you can see this is how the building is reacting. So the wave starts from the bottom of your model. So that's an input acceleration. And then when it reaches the top of your surface, it gets amplified. And as and when it goes to the surface, or it goes to the top of your building, it gets more amplified. So hence you can see more acceleration on the top of your building. So I would like to draw an acceleration versus time for this model. And as I said, the roof is not important for now. Hence, I have deactivated the roof. So let's go for extraction. So here we have an extract option to extract whatever results that you are interested in. Let's go for actual deformation. Yeah. So here, go for seismic analysis. I have given the name as seismic. And now accelerations. In the results, we need to go for TX acceleration. And I'm not interested in results in maximum, absolute maximum, and minimum. So just want to check the result from first step to last step. So just consider a node at the bottom, and let's ask software to show you the table. So this is the input acceleration, but let's say on the surface now. So we have selected two nodes, so you'll be getting two tables. So here we have, let's draw a graph. Yeah, so here on the surface, the green curve is your input acceleration, and the red one is your acceleration on the top of the soil. As you can see, the peak input acceleration is around 1.29 meter per second square. In what we have seen in the input is in terms of g, that means in terms of z. Now it is in terms of meter per second square. Hence, it's 1.29, and the maximum is 3.37. 3.37 here. So you can see it has changed from 1.29 to 3.37. The acceleration has been amplified on the top of your building. Sorry, on the top of your, let's say, ground. Now, let's consider a node on the top of the building. So I have considered a node on the top of the building. Let's ask the software to show the table. So we have three with us. Just select all the three columns and ask the software to show the graph. The blue one is your input. The green one is your acceleration on the top of the ground surface, and the red one is the acceleration on the top of the building. Now it reached to a value of 5.28, so which is very high. 5.28, that means the acceleration has been increased from 1.29 to 5.28. Yeah, so the amplification value is 5.28 upon 1.29. So that's the amplification value, and it's very high. So it's more than 3 times. Now let's check how the displacement varies. So for the displacement, you need to go for relative displacements now. So when you run the analysis, the software, when you go for ground acceleration, so at the bottom, bottom part also deflects, because you're running an time history analysis, but we are not interested in the bottom part. Hence, we will reduce all the values with respect to bottom displacement. Hence, we need to go for relative displacement. So now go to TX translation, and all the same nodes, we are going to consider the same nodes. So this node on the ground surface, bottom node, and we have top node on the building. As you know, since I'm going for relative displacement, this bottom node will provide us with a zero displacement result. So that's what we are going to get. We'll see once again. So here you go. You have all zero values since it's a relative displacement. So still, just ask this. We are asking the software to go for a graph. So since it's a relative displacement on the bottom node, it's zero, and the displacement on the ground surface, the maximum displacement is around 0.07 meter. Here the results are in meter, and then the maximum displacement on the top of the building is 0.12 meter. Which is very, very high. If you are going to consider the nonlinear material for the building, then it's definitely going to get failed. But since I have considered elastic material for the buildings, you can find a huge values over there. But if you're going to consider nonlinear material and provide the software an essential yield stress, then I think this model would get failed. And you can even ask the software to show the plastic status as well. So this is how you can extract the results for acceleration, and you can extract the results for the displacement. So this is your plastic status, where most of your building is under unloading failure. Since it's a Moore-Coulomb model, of course we can face this unloading failure. So let's get back to the presentation now. So now we have done the analysis and we have seen the results as well. So we'll just look after what we have done till now. As I said, we first ran the eigenvalue analysis, and hence using the first mode 1 and mode 2 frequencies, which in this model is 3 and 4 modes, and we considered the frequencies corresponding to mode 1 and mode 2, and we ran time history analysis considering these two modes. Why we have considered 3-4 modes is because these two modes are having high participation, high mass participation. So now this is our model, and we generated acceleration versus time as well as displacement versus time results. Now we'll see what are the additional tools that are present in GTS NX that will be very much helpful for dynamic analysis. The very first one is GTS NX inbuilt have a tool called free field analysis, which is nothing but 1D ground response analysis tool. So here in this tool, this analysis does not consider the interaction between superstructure and the soil. We are purely inputting the soil materials such as the shear wave velocity and the unit weight and so on. And for each and every layer of your soil, the corresponding modulus reduction curve and damping ratio curves needs to be inputted. So once you run the analysis, you can find the variation of damping ratio with respect to depth and variation of shear modulus with respect to depth and so on. So this actually this 1D ground response analysis is very important tool, and many cases this tool is using this tool we calibrate the results of our time history analysis finite element model with this results. So hence we have this free field analysis tool directly inputted in the GTS NX. So using this tool, you can deconvolute. I have explained the deconvolution concept earlier. So you can deconvolute using this tool. This tool is similar to Shake software and Deep Soil software as well. And now we have artificial earthquake generator. So here, what it actually does is it converts the design response spectrum into compatible time history. So we have a design response spectrum compatible time history. So many cases where we want to apply the earthquake at X location, and we need to convert that X location earthquake data to apply and apply it in the location Y. So we cannot directly apply the X location earthquake on the Y location because the acceleration of that particular ground is different. So we need to do some characterization. So that's another concept, but we have another concept called artificial earthquake data. What it actually does is we have, according to code, a particular area based on zones, you can have one design response spectrum. So using that design response spectrum, this artificial earthquake data, generated can convert that design spectrum into compatible time history using a trapezoidal function in GTS NX. So this time history can be applied to your model of that particular area, and you can find you can run a detailed analysis for time history. So how the behavior of the model is, what is the frequencies, and how the acceleration is varying with respect to time. So all those stuff can be done using this with artificial earthquake generator. So you can use this artificial earthquake in order to convert your response spectrum to corresponding time history. And we have a blasting and trine load data generator as well. So as you know, generation of the dynamic load is an tedious task. In case of earthquakes, GTS NX has a database long list of earthquake data present in the software, and here in case of blasting, still we have some good tool called blasting load generator. So how can you generate the blasting load, that is force with respect to time, is using the equation. So we have the equations which are used across the world. So you can use those equations and input the blasting velocities, explosive densities, and the corresponding parameters, and you can find load versus time blasting curve. So you can apply this load in your model, and using that load, you can find the effect of your blasting on your adjacent structure, or because of that blasting, what is actually happening in the model, and so on. And another important tool called train dynamic load table. So with the advent of this high-speed railway trains in many countries, we can no longer consider the train dynamic load as a static load, as an equivalent static load. We need to consider that as a dynamic load itself. So in order to consider that dynamic load, the manual calculation is highly tedious task, because train dynamic load is dynamic in terms of space and in terms of time. So with respect to space, it varies. With respect to load, with respect to time as well, it varies. Hence, we have this train dynamic load data table with us. You can choose the type of train, or you can input your own train data with here. So distance between the axles and the force on each axle, and the velocity of the train, and ask the software to show the graphs. So this is with respect to space. At each and every node, what is the variation of force versus time. So this is with respect to space, this is with respect to time. So another important analysis is liquefaction analysis. As I said, the effect of earthquake can be liquefaction, or a landslide, or tsunami, and many more. So here in GTS NX, we can perform both landslide analysis as well as liquefaction analysis. So here, generally, what is liquefaction? So if we have a sand layer, and then it is a saturation condition, because of earthquake, the pore pressure develops very high, drastically, and because of that pore pressure, in some cases, this pore pressure equals to your total pressure. So when it equals to your total pressure, it's your shear strength becomes zero, and when shear strength becomes zero, your soil layer will act like an liquefiable layer. So in that cases, after earthquake, you may find unequal settlements of your building or structure, and if you have unequal settlement, it results in cracking of your building and eventually the failure of the structure. So but important thing in order to avoid liquefaction is a proper pile foundation. So we need to go for pile foundation is best technique for liquefaction. That's another scenario altogether, another topic. But in order to simulate this liquefaction analysis, we have two material models in GTS NX. We have modified UBC sand, and we are also having PM4 sand materials with us. So using these materials, you can simulate the liquefaction analysis. As you can see, this layer is a liquefiable layer. I'm exaggerating the results over here. This is an liquefiable layer.